So we finished out-of-order execution and data flow last time. This was one example of an execution model, right? Data flow is an execution model where everything is data-driven, exposed to the programmer. Out-of-order execution is an execution model where everything is control flow, except underneath you do restricted data flow. So you know all of that very well by now. Any questions on out-of-order data flow concepts? Okay. You'll study that a lot for the exam next week. So as a reminder that the exam is next Wednesday, March 5th. Hopefully you'll all ace it. I see a lot of excitement. And for preparation for the exam, well, I'll talk about this on Wednesday, but you can start looking at the past exam questions. That's a very valuable source, because the questions will be similar in nature. Of course, it won't be the exact same question, but if you know how to solve those problems, you'll see that those problems are really testing understanding of the material and the ability to apply the material that you learned to problems. So I won't test you on memorization. Really, I'll test you on whether you understand the material. And take a look at the questions, definitely, from the past 2 years. You can even take a look at the questions from 740, because the style of the questions are relatively similar. OK, can everybody see this in the back? Yes? OK, good. Because I can't see it very well, but that's OK. As long as you can see it, that's the important part. OK, today we'll cover another execution model. Actually, this will span 2 lectures. Single instruction multiple data execution model, and GPUs, which are a form of single instruction multiple data. But we'll mainly cover SIMD today. Before that, a reminder, Lab 4 is out. This is the exact same slide, except for this part that I used in the last lecture. Lab 4B is also out, and I still recommend that you get started early, even though you have 4 weeks. It's better to do these separately. And actually, these are independent, so you can do these out of order also. There's no control flow ordering between these two. OK, these are the readings for today. So hopefully you're doing readings. We'll talk about SIMD parallelism, or SIMD processing, how to exploit regular data parallelism. So far, we've looked at a lot of irregular data parallelism, right? I told you that data flow is an execution model that is exceptionally good at exploiting irregular parallelism. What does irregular parallelism mean? Some instructions are dependent on each other, and you somehow figure that out. Right? Regular data parallelism is pretty much exactly the opposite. Parallelism is very regular. We'll see what this means soon. But first, I'll start with Flynns Taxonomy of computers. Mike Flynn from Stanford, who did a lot of contributions to computer arithmetic and computer architecture, classified computers into 4 classes in 1966, based on what does an instruction operate on, basically, and how many instruction streams you execute on a computer. SISD is a single instruction operates on a single data element, or multiple single data elements. This is basically what we've seen earlier, right? If you have an instruction that operates on 2 registers, that's single. 2 scalar registers, that's SISD, right? Single instruction operates on really single piece of data elements. SIMD, we will see today, here the single instruction operates on multiple data elements. When you specify a register, it doesn't specify only a single element, but specifies a host of elements, a vector of elements, or an array of elements. Does that make sense? Not a single piece of data, but an array of data, maybe 1,024 pieces of data. And when you say add, that add specifies not an addition on 2 pieces of data, but it specifies an addition of 1,024 pieces of data. Make sense? So you can now add, with a single instruction, 2 vectors. That's the idea. So if you're doing addition on 2 vectors, you can specify this with a single instruction, such that you don't need to waste 1,000 instructions, in other words. That's the idea. Because you're repeating the same operation on multiple data elements. And this is very useful in graphics, for example. That's why graphics processing units today use this model. Because let's assume that you're displaying an image in graphics. You're basically loading a bunch of different pixels somewhere, right? If you say load 1,000,000 elements, and you can specify that with a single instruction, that's very efficient. As opposed to SISD, load a million elements, you need to do a million loads, one by one. So that's the basic difference. And we're going to cover this in detail today. And we're going to look at two forms of it, an array processor and a vector processor. And you'll see the difference at the beginning of the lecture. So this is actually a classification, right? What kind of a data element does an instruction operate on? You can have two dimensions or two values for each. You can have basically instruction dimension and the data dimension. An instruction can be single instruction or multiple instructions. Data dimension can be single data or multiple data. This is SIMD over here. This is basically the sequential execution model that we've seen. SIMD is over here, we've just talked about. There's also a MISD, which is kind of odd actually. Multiple instructions operating on a single data element. It's a little bit hard to think of. You have multiple instructions, single data element somehow being transformed by multiple instructions. Closest form is really a systolic array processor, a streaming processor that we will talk about later on. Actually, the earliest systolic array processors were developed at CMU in the late 1970s, early 1980s by H.T. Kung. MIMD is basically multiple instructions operating on multiple data elements. If I do this over here, this is basically a multiprocessor. You have multiple independent instruction streams operating on multiple different data elements. And this is what we've seen earlier. A multi-threaded processor is an example of this, or a multiprocessor. Multi-core processors are examples of this. So in this course, actually, we're going to cover all of these models. But today, we're going to cover this model. And all of these models have advantages and disadvantages. This is actually great at exploiting regular parallelism. If you can specify your program to be coded with SIMD instructions, you can make it very, very efficient. But your problem needs to be amenable for that. If you're operating on huge vectors, then that's great. OK, so what is data parallelism? Let's focus on that. In data parallelism, the concurrency or parallelism really arises from performing the same operation on multiple different data elements. That's why it's called single instruction multiple data. And an example is dot product of two vectors, or an addition of two vectors. We'll see this example coded today. Contrast this with data flow. In data flow, concurrency really arises from executing different operations in parallel, right, in a data-driven manner. It's not really multiple different pieces of data, same operation on multiple different pieces of data elements. Right? You could have a data flow graph encoding the same operation on multiple different pieces of data elements, but they will be individual nodes. Right? An individual node in data flow operates on single data. Yes?
So would data flow be MIMD?
Well, that's a good question, actually. Data flow, people have classified data flow as MIMD also sometimes. It depends. You really are executing multiple instructions in multiple data. So I would argue that it's closer to MIMD than SISD. But if you look at each instruction, it's really an instruction operates on a single piece of data elements. Right? I won't ask you to classify data flow. This is actually a good rule of thumb, but sometimes it's very difficult to classify some of the models into those, fit those into four. And today, many computers actually use a combination of the multiple models. For example, the x86, many x86 processors, well, all x86 processors have extensions to x86, which are, I don't know what they're called right now, but they used to be SSE. Initially, they were MMX. These are multimedia extensions that we will cover. They're SIMD operations, basically, in a SISD, in a control flow ISA. Contrast this with thread or control parallelism. This is definitely MIMD if you have multiple threads. In this case, the concurrency arises from executing different threads of control in parallel in a multi-threaded program. Right? It's not the same thing as this. SIMD exploits really instruction-level parallelism. Now you have multiple instructions. Think of these operations as instructions. They are concurrently operating on multiple different pieces of data elements. Right? Instructions just happen to be the same. Right? If you're doing add on two vectors, you're doing many, many adds on individual elements of the vectors. OK. This single instruction operating on multiple data elements can happen in time or in space. Actually, that's true for all of the models, if you think of it. You can do multi-threading in time or space. Right? You can have multiple threads executing in parallel, or you can multi-thread. Time multiplex, the same hardware. just like we saw in fine-grained multithreading. It's true for SIMD also. The instruction can operate on multiple data elements in time or space. You can, for example, add 2 vectors, and each element can be added, multiple different elements can be added in parallel at the same time, or they could be added in time, over time. You can use the same adder to multiplex the independent additions. Normally, you have multiple processing elements, as we will see. So this leads to the time-space duality, and this leads to the distinction between an array processor and a vector processor. This is a purist distinction, as I will talk to you about later. All processors today, including the GPUs, are a combination of both. They're both vector processors and array processors. If an array processor, a SIMD instruction, a single instruction, operates on multiple data elements at the same time. Basically, all of those operations are done in parallel at different functional units. In a vector processor, the instruction operates on multiple data elements in consecutive time steps. Let's take a look at an example of this. Basically, this is what a vector processor or a SIMD processor code looks like. This is, think about this as an array with 4 entries, right? 4 elements. You can load that into a register, which can have space, which has space for 4 entries, 4 elements. And then you can add 1 to that register, which means that you increment every single element here by 1 in parallel. Basically, you're specifying 4 adds with this add instruction. And then you can multiply the resulting vector register by 2. Again, 4 multiplies. And then you can store the vector register back to where you load it, back to the array. And you're doing 4 stores. Basically, each of these operations specify 4. Each of these instructions, vector instructions, if you will, specify 4 operations. So you can do all of these 4 operations specified by an instruction in parallel. That's what an array processor does. Or consecutively in every cycle. So if you look at this, in the array processor, it executes the 4 load operations in parallel. Load on element A0, load on element A1, load on element A2, and load element A3 in parallel. And then you can do the adds in parallel. And then you can do the multiplies in parallel. And then you can do the stores in parallel. Make sense? Whereas a vector processor does the operations in a pipeline manner. You do the load on first element of A first in the first cycle. In the next cycle, now you can load the next element of A, A1. While you're doing that, you can add the first element of A. You can increment, basically. And then in the next cycle, you load the second element while you're adding the first element, while multiplying the first 0th element, I guess. And then the next cycle, you load the third element while adding the second one, multiplying the first one, and storing the 0th one. And then you can drain the pipeline this way. Does that make sense? So if you look at this, in an array processor, same operation is executed at the same time. In a vector processor, you see different operations executed at the same time. That's the time-space duality. If you look at space, basically this is what the space looks like in an array processor, right? You have different operations in the same space. Space meaning the processing element, which means that the different processing elements need to be capable of doing all of the operations. Now you can physically implement in a different way, but you do need to support this. Whereas here, you always do the same operation in the same space. Make sense? So immediately, I guess one question is here, obviously, the hardware is much less here, right? Because you only need 1 load unit. If you're doing 1 load operation at a given time, you only need 1 load unit. If you're doing multiple load operations at the same time, you need multiple load units. So this is, by nature, more expensive in terms of hardware cost, because you need to support multiple operations at the same, multiple of the same operation at the same time. Okay. Okay. So as you will see later, modern GPUs are a combination of both. You do both the same operation at the same time and same operation at the same space. Well, I didn't say that right. Basically, you both pipeline the same operation over cycles, as well as do the same operation at the same time, because your vectors are much larger than what you can actually reasonably implement in hardware. OK. Yes?
So you can only do as many elements in parallel as your largest vector register?
That's correct, with a vector instruction, yes. But we'll get to that. What if your vector is much larger than that? Then you need to actually code loops. OK. So what's the difference between this and VLIW? Remember, we talked about VLIW, very long instruction word, where an instruction it actually encodes multiple operations, right? And compiler packs those multiple operations such that they're independent of each other, and the hardware can simply execute them, right, without checking for the dependencies. This is what a VLIW processor conceptually looks like. You index into the program memory, and with a single program counter, you can get multiple operations that are completely different from each other. With a vector processor, let's take a look at the array processor. An instruction again specifies multiple operations, but it's much more compact. It specifies multiple operations that are really the same. Here, the operations can be add, load, multiply. In a vector processor or array processor, it's not that way. You basically specify an add on a vector register. Vector length is 4, let's say. This means that you do 4 adds on different data elements, different parts of the vector register. 0th element, first element, second element, third element. So instruction encoding can be much more compact. With a single instruction encoding, you can actually do many operations. OK. So what is a vector? I guess I've assumed that you know a vector, but it's really a one-dimensional array of numbers, right? Array of something, actually. They don't have to be numbers. But I'll assume that we have numbers in this case. And many scientific or commercial programs actually use vectors. Whenever you have this form of parallelism, SIMD processing is great. And think if you want to imagine one program, graphics is one of them. Think about, for example, zooming into an image. What you really do when you zoom into an image or zooming out of an image, you're really averaging a bunch of pixels that are nearby each other, right? And you're doing this across the entire image. So you have lots of parallelism in the data because all of those parts of the entire image are exactly parallel, right? They're independent of each other. You can do all of those operations in parallel. OK. A vector processor is one whose instructions operate on vectors rather than scalar values. And that's the main difference between what we've seen before. Before, we've seen scalar processors. Now, the instructions really operate on vectors. What are the basic requirements to build this? First, you need to be able to load or store vectors, assuming you have a load-store ISA, right? You could imagine a memory-to-memory vector processor too, but we're not going to assume that. So you need vector registers, basically, for this. You need to operate on vectors of different lengths. You don't want to limit yourself to a fixed length, right? Which means that you need to have a vector length register that specifies a vector length. And this should be software programmable. And one very important thing is to improve programmability, you want the ability to get the vector to be able to store the vector in different places in memory. So basically, the elements of a vector should not be consecutive in memory. And we will see this. If you think about, for example, you're multiplying two matrices. You can, for example, if you're multiplying two matrices, I'll give you this, I guess. Let's say you have two matrices. This is the example I'll use later on, I think. A, B. How do you do matrix multiplication? What you do is you get a row of matrix A. Let's say you want to compute product AB. You get a row of A and compute the dot product of this row with this column of B, right? And then you take the row of A and compute the dot product of it with the second column of row B, and dot, 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 and then form another array. If this is n by m and this is m by t, you form another matrix that's of n by t, right? OK. So if you would like to do that, if you need to ensure that all of these elements are consecutive in memory, you have one storage for B. But what if you want to later multiply B with some other vector? It doesn't matter what. You need to be able to take a row of B and multiply with a column of some other vector, right? If your vector processor requires that the elements of a vector are consecutive in memory, sometimes you're accessing this vector and the elements need to be consecutive. And sometimes you're accessing this vector, and the elements need to be consecutive. Well, you cannot satisfy both requirements, right? So to improve flexibility, vector processors also have something called a vector stride register, which specifies how far apart the elements are from each other of a vector. And you can set this by programming it. It's the distance between two elements of a vector in memory. So if you think about this, we'll get back to this with a slide. But if you look at B, let's assume that it starts from address B, and it's laid out this way: 0, 1, 2, 3, 4. Let's assume we have 10 elements, 9. And the 10th one is here: 10, 11, 19, 20, 21, 29, 30, 39. You get the gist of it. Now, if you want to load this vector, you can specify the stride. These are memory addresses at which the elements are located. If you want to load this vector into a vector register, you can specify the stride to be 1, because the distance in terms of addresses of the consecutive elements is 1, right? Where if you want to load this vector, in the original example that I showed you, you can change the stride to be 10, right? If you look at this, the distance between the memory addresses of the consecutive elements of this particular vector is really 10. 0, 10, 20, 30. Now, just by changing the stride register, you can enable the loading of different vectors. You just need to, the only thing you need to ensure is the distance between two elements remains constant. And you know that distance as a programmer. Make sense? Now, that actually reduces programmability also, right? You have to ensure somehow the vectors, the distance between two elements, stay constant. And we'll try to fix that later on. OK? So these three registers, well, definitely general purpose registers, vector length register and vector stride register, are necessary. We will see there's one more register, actually, not here, but a little bit later. OK, is this clear? Good. So a vector instruction, I've already told you, that performs an operation on each element in consecutive cycles. We're going to assume vector processors for now, for a while. Vector functional units are pipelined, so that you can actually pipeline the operation on a single vector. Because if you think about this, the operations that are performed on different elements of the vector are actually independent of each other. There's no need for dependency checking, because each pipeline stage operates on a different data element. And vector instructions allow deeper pipelines because of what I just said. There is no dependency inter-vector. Whenever you say, let's say, add 1 to each element of this vector, all of those operations that are specified by that vector add are independent of each other, which means that there is no need for hardware interlocking within a vector, right? It's beautiful. That's the data parallelism. No control flow within a vector also. And you can have a known stride. If you have a known stride, this enables the prefetching of vectors into cache and memory. You can pre-compute all of those addresses, and you can bring them into the cache. And by the time the vector operation gets to that element is already in the cache, right? That's the beauty of this regularity in code as well as program behavior. So let's take a look at the advantages and disadvantages of it before we go into the depths of it. The big advantage is no dependencies within a vector, right? This enables both pipelining within functional units and parallelization across functional units. Now you can have very deep pipelines because you don't need to deal with dependencies, right? Within a vector, again. Each instruction generates a lot of work. So you don't have a problem with parallelism, assuming your program actually has that parallelism. And this actually reduces instruction fetch bandwidth requirements, right? With a single instruction, you specify 1,000,000 operations if your vector length is 1,000,000, right? Which is great because you're really now amortizing the overhead of fetching that instruction, fetching 1,000,000 instructions, decoding 1,000,000 instructions, and maybe renaming 1,000,000 instructions. All of that front-end work that you need to do for an instruction is gone now. You do it only once and amortize the cost across 1,000,000 data elements. You get a highly irregular memory access pattern, assuming everything is strided nicely. And we will see that this enables parallel accesses. Actually, you need to have parallel memory systems to enable parallel accesses. If you want to load a vector, for example, that's of length 10, you would like to be able to load each element right, in consecutive cycles in a vector processor, in the same cycle in an array processor. And if you have a regular memory access pattern, you can do that distribution of data to different memory parts or banks much more easily. And as I told you, that regular memory access pattern enables better prefetching, easier prefetching. So we'll take a look at interleaving multiple banks. We'll cover memory in a lot more detail later on, but we'll have to cover it while talking about vector processors, because this is a really important part of the system in a vector processor. Don't get me wrong, it's a really important part of every system today, but especially important for a vector processor because you may need to load huge vectors, right? And you do need to load them quickly because you're operating on them at the same time, operating on the different elements of the vector at the same time. Another advantage that reduces instruction count as well as difficulties that we've tried to alleviate early on, branches, for example, is you don't need to explicitly code loops in a vector processor. Right? For example, if you're adding two 64-element vectors, now you can specify that with a vector add, with a vector length of 64. No need for a for loop, no need for branches. Right? It's kind of nice. And we'll see that this reduces the instruction count as well. Well, disadvantages, I guess I've shown you this. I would have asked you otherwise. It's limited, right? Basically, this works if parallelism is regular. If you have this form of parallelism, data or SIMD or vector parallelism, or as I'll tell you later, vectorizable code, this is great. Then vector operations are actually a huge plus. I cannot add more pluses over here, perhaps, because you really amortize. This really works greatly if you have this kind of parallelism. If you're adding two vectors, two arrays, multiplying, doing operations on huge pieces of data, the same operation. But it's very inefficient if parallelism is actually irregular. If you don't have this, if you're operating on scalar values, and still you may have really good parallelism, except you're not operating, a single instruction is not doing operations on multiple data elements, well, you're back to what we've discussed earlier. You cannot exploit it with this kind of machine. For example, if you're searching for a key in a linked list, this is a very difficult to vectorize operation because you have dependencies on every access, right? Well, because of this, a paper that I'm going to recommend to you later, written by Josh Fisher, says this. This is actually Josh Fisher's paper, which introduced in 1983 the very long instruction word architectures. Actually, vector processors were introduced a lot earlier than very long instruction word architectures. And while introducing very long instruction word architectures, remember this is a single operation, a single instruction specifies multiple different data operations. And those data operations, well, those operations are packed together by the compiler and ensured to be independent of each other. To motivate this kind of architecture, this is what Josh Fisher said. To program a vector machine, the compiler or handcoder must make the data structures in the code fit nearly exactly the regular structure built into the hardware, which means that you have to have somehow vectors, right? That's hard to do in the first place, assuming that your problem is not like graphics, for example, and just as hard to change. One tweak, and we will see what that tweak is when we talk about the memory system, and the low-level code has to be rewritten by a very smart and dedicated programmer who knows the hardware and often the subtleties of the application area. So for example, if you're loading a bunch of elements in a vector, and these elements do not happen to be in the same memory bank, well, you cannot load them in parallel, right? You need to wait for one element to be loaded for the next element to be loaded. And if the machine structure changes a little bit such that you have more banks or fewer banks, well, now the programmer needs to, if you want to get high performance, you need to rewrite your code such that you can do those operations in parallel. OK? Does that make sense to people? OK. OK. Another limitation, this is not a disadvantage necessarily, but a limitation, because there's so much parallelism specified by large vectors, memory, especially bandwidth, can easily become a bottleneck, especially if the compute memory operation balance is not maintained, if you're doing lots of loads and very few computation on those loads. And especially if data is not mapped appropriately to memory banks. This is exactly what I told you earlier. If these different pieces of elements are not mapped to different banks, well, Now you're waiting for memory most of the time. Because of this, vector processors, a lot of the memory innovations in memory like banking, interleaving, or the mechanisms to map these data elements to different banks, both in terms of compiler and hardware, were developed in the context of vector processors for a long time. Now they're used in regular processors today, but those mechanisms to improve memory bandwidth, as well as map data such that you can make the most out of your memory bandwidth, were developed initially for vector processors. OK, any questions so far before we go into some code examples to see why this is advantageous? OK, well, before that, I guess we'll go into a little bit more instruction set for the vector architecture. So what does a vector register look like? Basically, it looks like this. This is vector register 0. It holds n m-bit values. M-bit could be 64 bits, for example. But n is the biggest vector an instruction can operate on. Here you see that you have 0 to n elements in this vector register. And you have a bunch of vector registers in a machine. There are 3 control registers, 2 of which I talked about, vector length and vector stride. I'll talk about vector mask also. Maximum vector length can be n, but the programmer can specify it to be smaller. For example, if you're operating on a scalar value, you can specify this vector length to be 1. Right? You can just operate on 0th element, and all of the other elements you can ignore. Right? Again, you can specify the vector length to be anywhere between 1 to n here. Vector stride register we've talked about. Basically, you can change the stride to any value. And this specifies for a load or store instruction what is the distance between consecutive elements. And we will see how this is used when you're actually generating addresses to load consecutive elements. But it's really easy, right? You have a base register. And to be able to load a vector of vector length, you keep adding the stride to the base register and incrementing the base register by the stride, vector length times. Right? We'll see that. Vector mask register, this enables conditional operations on a vector. It's actually predicated execution. I should have asked you after I introduced this. But this indicates which elements of a vector an instruction should operate on. Because you may not always want to operate on all elements of a vector. When you say an add, you may want to add some of these elements together, because you may be adding conditionally, right? And condition may be dependent on something else. And we'll see that. This is the same as conditional execution, predicated execution. In fact, you could consider that predicated execution was developed within the context of vector machines. And vector mask specifies whether this element should be operated on or not. Okay? This is set by vector test instructions. For example, a vector test instruction looks like this. You set vector mask is a 1-bit register that's as wide as a vector data register. So you have n bits here. And you set that by testing some condition on a vector register. Right? Or you can set it to all ones, in which case all of the operations are unconditional. Or all zeros, then you don't operate on it. But why do you even do that? OK. So let's take a look at vector functional units. We'll see several code examples with vector mask registers soon. What does a vector functional unit look like? Basically, assume that these are vector registers. You can pipeline the functional units as long as you want to execute operations on different elements. And if you look at this, in this case, I show you a 6-stage multiply pipeline. You can feed the elements of vector registers. In this case, it's vector 1, vector register 1, vector register 2 as inputs to the functional unit. And different elements can be in different stages. Basically, if you're when the pipeline is full, the 0th element of vector 1 and vector 2 is being added at the last stage. The first element is here. The second element is here. Third element is here. Fifth element is here. And sixth element is here. Make sense? You can basically stream consecutive elements from the vector registers into the vector functional unit, and then write it back, stream it back into the destination register. So it's kind of a beautiful paradigm. This is one of the other reasons GPUs are called streaming processors. You're really streaming elements from these huge registers one by one into the functional units and streaming data out into the destination register. Because each element, each consecutive element is independent within a vector, you don't need to check for any dependencies in this pipeline, right? I guess one question over here is, does it make sense to increase your pipeline length beyond vector length? It does improve your throughput, right? So probably not. Unless you can have independent vectors pipeline into the same adder. But now you need to check for dependencies if that's the case. OK. I'll give you one of the oldest vector machines. This is Cray I. It was published in 1978, but it was developed in early to late 1970s. It looks kind of exact like this, actually. You have a bunch of vector registers. They go to these different vector functional units. If you cannot read them, this is an add, logical, and I cannot even read that. I need better eyes. Shift, you can read that. Wow. You want to exchange our eyes? OK. This is basically the vector part of the machine. And it actually had scalar and vector modes. Basically, it did have scalar registers, too. It didn't give up. Because it's very inefficient to execute in vector mode if you're doing scalar operations. Setting the vector length to 1 is just not a good idea. Because you're doing many operations, right? Except you're masking them out. Because those functional units are there. And we'll see that in a little bit. It had 8 64-element vector registers, and each element was 64 bits. It had 16 memory banks. This was actually one of the biggest memory systems at its time. It also had scalar registers, 8 scalar registers, and 8 address registers. Address registers were used to access memory. So you can see that, I don't know if it's shown here, but you can actually have a stride here and different address registers and different strides operating on those address registers. I'll show you this in a little bit. Well, one thing to remember is this scalar part of the machine was really important. In fact, Cray designers took extra care to ensure that this was the fastest scalar machine in the world at that time. Can anyone guess why? This was an exam question, I think, last year. Remember, you remember Amdahl's law, right? Here, think about a perfectly parallelizable program. You have 64 elements, right? You can speed up the perfectly parallelizable part by 64 times. But if your perfectly parallelizable part is not a huge chunk of your entire program, you're limited by the scalar part of your machine. Right? The performance improvement you'll get is limited by the scalar part of your machine. Make sense? So they wanted to ensure that the scalar part is not a bottleneck for the execution of the entire code. So they ensured that this was the fastest machine of its time. We'll get back to that also. OK. So memory banking, I talked about banks, and you see that there are banks over here somewhere. Yeah, actually, I don't see them, but that's OK. Well, I guess you have 8 address registers here, but that's OK. Memory is divided into banks that can be accessed independently. And banks share address and data buses. This is one example of this. You have 16 banks. This was actually similar to what Cray's memory system looked like. And each bank has a memory data register and memory address register. And the banks, for cost reasons, they're not completely independent. You can access the arrays independently, but you cannot start an access to 2 arrays at the same time, because they share this expensive data bus and this a little bit less expensive, but still expensive address bus. Basically, what you can do is you can start one bank access per cycle, and the next cycle you can start the next bank access. This is called memory banking, or memory interleaving also. You can also complete one bank access per cycle because the data bus is shared. Right? Which means that you can sustain n parallel accesses if they go to different banks. In this case, you can sustain 16 parallel accesses. OK? So if you want to ensure that you saturate your memory, you want to have more banks than the latency of access for one bank. Right? In Cray I, for example, memory bank access latency was 11 cycles. And that's exactly why they wanted to have 16 banks. Because if a bank takes 11 cycles, by having 16 banks, you can ensure that you can fully overlap that 11 cycle latency, right? Every cycle you start one access, and by the time you start the 12th access, the first access is done. Actually, you really need only 11 banks in that case, right? Except 11 is a very weird number to implement in binary logic. Even calculating the address will become difficult. Okay, that's why they had 16. If they had 8, even though they may have a vector load that has 11, let's say, that has 11 elements, they would have had to stall because the memory system would be a bottleneck, right? Having 8 banks with an 11 cycle bank access latency makes the memory system a bottleneck quickly because you're stalling for the next 3 elements. OK. So a vector memory system actually looks like this. We can think of this over here as memory banks. But whenever you do a vector load or a vector store, what happens is the base address of the vector load, as we will see later, is put here. The stride is put here. And in consecutive cycles, you take the base address, you add the stride to it, and change the base address to be base plus stride. In the next cycle, you have base plus stride here in this register, and you add to it the stride, you get base plus 2 stride, right? In the next cycle, you get base plus 3 stride, base plus 4 stride, dot, dot, dot. You do this until, well, what is not shown here is the vector length, until you exhaust the vector length, right? Now you can load as many addresses as your vector length specifies. But the addresses, of course, need to be regular, right? They need to be strided from the base address with this stride. And this stride comes from the vector stride register. And the data can go to the vector register in a pipeline manner, right? You can load element 0. And of course, this works nicely. You can overlap the latencies if your addresses are mapped such that vector element 0 is here, 1 is here, 2 is here, 3 is here, 4 is here, 5 is here, 6 is here, 7 is here. If your vector element 0 is here and 1 is here in the same bank, well, too bad. You cannot load them in consecutive cycles, right? That's why mapping of vector elements into these different banks makes a huge difference. In today's GPUs, for example, when you program GPUs, how you map your arrays into the memory system makes a huge difference in terms of performance. If you get bank conflicts, then you don't get good performance. OK. OK, let's take a look at why actually, what kind of performance benefits can you see with this vector processing. I'll give you this really simple example where we're trying to average 2 arrays, basically array AI and BI. You basically add the elements of array and BI and divide it by 2. And C is you can think of this element by element average of the 2 arrays. How long does it take to execute this code in a scalar machine? Well, I've given you the code over here. And I made some assumptions. But these are basically setting up. In this case, your vector length is 50, right? Each vector is 50. It has 50 elements. So in a scalar machine, you don't have vector operations. So this will be our loop boundary. We'll check this to see if the loop is done. And we load addresses A, B, and C into R1, R2, and R3. This is a setup code. And assume that the moves take 1 cycle each. And then we have this loop that's coded. In this case, first, we want to load the first element of address from address A. That's what this operation specifies. It's a load. I'm not going to go through this in detail. And then you load the second element, the first element of vector B. And we use auto-increment addressing, just so that we can reduce the instruction count rate. Because in this case, this is a nice case where auto-increment addressing, remember lecture 2 or 3, is useful because you have a nice strided access. You keep going to the next element. In the next iteration of the loop, you're going to load the next element. So R1 is modified to be R1 plus 1 with the same instruction here. And then this is the addition. And then this is the division by 2, shifting by 1. And then this is the store into C. And then this is the loop condition check. This is decrement and branch if not 0. So again, we combine multiple operations to minimize the instruction count over here. And these are the instruction latencies. I'm going to assume latencies that are similar to Cray I, 11 cycles for load, 11 cycles for store, assuming no bank conflicts. And an add is 4 cycles, shift is 1 cycle, and this branch, decrement, and branch, if not 0, is 2 cycles. Okay? This is the loop code and scalar instruction stream. You don't need to convince yourself here, but you can take a look at it later. But it takes 304 dynamic instructions. Basically, you need to execute this loop 50 times, and you need to decode this load, fetch this load, and decode it 50 times. And as a result, you have a total of 304 instructions, 300 in the loop, 4 over here. What is the execution time of this? I'm going to go through, breeze through this and make some assumptions. You can actually obviously optimize this. But if you have an in-order processor with a one bank memory, single bank memory, what happens is these first 2 loads cannot be done independently because they access the same bank, right? And you have dependencies all over here. As a result, these first 2 loads cannot be pipelined, so they take 2 times 11 cycles. And if you do the calculation, you basically add up these latencies, multiply them by 50 times, because you execute all of these operations 50 times. And these take 4 cycles, so you get 2004 cycles. If you have an in-order processor with 16 banks, and if you interleave memory, as I discussed earlier, if you word interleave, basically consecutive words are stored in consecutive banks, such that you can access 2 consecutive words in a pipeline manner. Now you can pipeline the first 2 loads, right? This load, while accessing it bank 0, this other load accesses bank 1. Again, there's another assumption here. These 2 map to different banks, right? The data elements they access map to different banks. And you can now imagine, this can get complicated, right? If you're accessing many arrays, you need to ensure that for the multiple loads to proceed in parallel, they need to be mapped to different places, right? Different banks. OK, in this case, it takes 1,504 cycles. And I'm sure you can optimize the in-order processor a little bit to reduce it. OK, why 16 banks? We already discussed this. Because we have 11-cycle memory access latency. Having 16 banks ensures that there are enough banks to overlap enough memory operations to cover memory latency. Let's take a look at the vector code for the same pseudocode over here. If you look at this as a vectorizable loop, what does a vectorizable loop mean? It's simple. If each iteration is independent of any other, the loop is vectorizable, at least fully vectorizable. If there's a loop carry dependence, if one iteration is dependent on a previous iteration, then that loop is not vectorizable. OK? It's simple. We can vectorize it because it satisfies this constraint over here, this property. So what does the vectorized loop look like? Well, it looks much nicer, actually. Basically, vector length, we know that it's 50. So we set the vector length to be 50. Vector stride, based on the assumption that I made earlier, is 1, because you keep accessing the consecutive elements. Now, the first instruction over here, you do a vector load from A into vector register 0. That loads the entire vector A into vector register 0. And the total latency of this instruction is, assuming the memory is word interleaved, consecutive words are in consecutive banks. To get the first word, it takes 11 cycles from the bank. Right? Now the remaining 49 words come in a pipeline manner, because they're actually in different banks. Right? You can start each access in a pipeline manner, and they complete in a pipeline manner. So this is the assumption. It'll take 11 plus vector length minus 1 cycles to finish the entire vector operation. In this case, vector length is 50, so it takes 60 cycles to load the entire vector into the vector register. The second one over here is another vector load. Now we're loading B into vector register 1. Again, it takes the same amount of time. The next instruction is a vector add instruction. Basically, we add vector 0 to vector 1, store the result into vector 2. And again, here, assuming that each add operation takes 4 cycles to get the first result, and an adder is pipeline, to get the first sum of the element, zeroth element of vector 0 and 0th element of vector 1, it takes 4 cycles. And all consecutive elements are pipelined. So it takes 49 more cycles to finish the entire vector operation. And then the next one is a shift. You can do the similar calculation. And then the next one is the store. You store V3, which is the result of this, into address, memory address C. Okay? So if you look at this, you have only 7 dynamic instructions, right? Instead of decoding, fetching 304 instructions, we do it for only 7 instructions. And we accomplish the same amount of work. This is why GPUs are very efficient today in executing parallel code. OK, now let's take a look at how long it takes to execute this. And we're going to progressively make it faster. First, I'm going to assume no chaining. I'm introducing another term here. But chaining is a fancy word for vector data forwarding. The key question is, can you forward the result of a vector functional unit to the input of another vector functional unit? And no vector chaining means that, no, you cannot do that. You don't have data bypassing support. Which means that the corollary is the entire vector register needs to be ready and needs to be finished, computed on, before any element of it can be used as part of another operation. This is a bad vector machine design, but we'll fix that. Right? Because if you think of it, vector register, even though you're operating on a huge vector register, you're really operating on it element by element. Right? Once the first element is ready, let's say you've actually added the first elements, you can do the shift on that element. You don't need to wait for the entire vector register. Right? But I'm going to assume that that support is not there yet. I'm going to assume 1 memory port, 1 address generator, and 16 memory banks, word interleaved, again. 1 memory port will be bad for this also, but not for this one. So how long does it take to execute all of these operations? Basically, this is the setup operations over here. And then we do the vector load for, I'm switching between them quickly, but vector load for A into vector 0, it takes 11 plus 49 cycles, right, to do the entire operation, as I just said. You do the second vector load from B to vector 1. Again, it takes 11 plus 49 cycles. And you cannot do these in a pipeline manner, or you cannot overlap this over here, because you have only 1 memory port. Right? And then you do the add, and then you do the shift, and then you do the store, all in a vector manner. But they all need to wait for each other because there is no chaining. Right? You cannot start at the end of this first element add, you cannot start the shift of that element. You cannot pipeline the add and shift because you don't do data forwarding. Even this kind of crippled vector machine takes 285 cycles. That's a huge difference from 1504, right? And this is kind of a crippled machine because that simple data forwarding is not done, right? And you have a kind of weak memory system. OK, so vector chaining, I've already told you this, but I'm going to demonstrate this pictorially also. This is basically data forwarding from one vector functional unit to another. If you look at this example, it's similar to the example that we've seen here. You're loading vector 1, and then you're multiplying vector 1 with vector 2, and storing the result into vector 3. And then you're adding vector 3 and vector 4 and storing the result into vector 5. If you look at this, these operations are dependent on each other. And if you think of this register as a whole vector register, not individual elements, you have to wait. This entire load needs to finish before this multiply can be started. But vector registers are really just element by element. So what we can do is, oh, wait a second. When the load unit returns the first element into the vector register, instead of waiting for all elements to be returned to this vector register, we can simply bypass or forward that element to the multiplier. Right? This is with the same forwarding that we've seen, done in a kind of a different way. And if you do this now, you can, while the load unit is returning the second element, now you can multiply the first element of V1 with the first element of V2. And while the load unit is returning the third element, you can multiply the second element of V1 with the second element of V2 and write the result into V3. Make sense? OK, this is a simple concept. It's called vector chain. And again, you can do it over here. You can chain the adder to the multiplier. When the multiplier finishes the first element, instead of waiting for all of the elements to be present in vector 3, that first element is supplied to the adder. And you can do the addition of the first element with the multiplication of the second element, and blah, blah. OK? OK, of course, this is not as simple as this, because if you would like to support this fully, you have to chain every unit to every other unit. Right? But that's true for any kind of forwarding you do in a pipeline machine also. OK, so with this, with just chaining, without changing the memory system, what do we get? Basically, now what we can do is, well, this is the memory system. We cannot parallelize these two load operations. And this was the add operation, if you remember. This is the addition of here, what we have is we've already loaded vector register 1 with the result with the vector from A. We've already loaded vector register 2 with the elements from B. But the first element arrives after 11 cycles. Here we can start the addition of A and B, right? Or vector register 1 and vector register 2, because first element of both of them are ready at this point. And that addition takes 4 cycles for the first element. And the remaining elements we can keep adding. Does that make sense? The first element of A and B are both ready over here, or vector register 1 and 2 are ready over here. If you switch to this code again, or I guess I use 0 and 1 over here, should be consistent. Let's go back. Yes. The first element of vector 0 and vector 1 are ready here, so you can start the add over here. The second element is ready in the next cycle, so you can start the add of that in the next cycle. The third element is ready over here, so you can start the add in the next cycle. Fourth element, ... And by the time you finish the fourth element here, the first addition is done. And you just need to finish 49 more additions over here. And when this addition finishes for the first element of V0 and V1, now you can shift the result, right, in one cycle by chaining that element to the input of the shifter. Right? You can actually start storing this element right here. Because at this point, the first element of both vectors is loaded. The first elements of both vectors are added together. And the result is shifted over here. Now you're ready to store that element. But I start the store over here. Because remember, the memory had only one port. We need to finish the load of the, I don't know how many number of elements over here, but definitely the 50th element, before we can start the store of the first elements. Because memory has only one port. Does that make sense? OK. With vector chaining, we're now down to 182 cycles from 285. Right? So chaining actually buys a lot of overlap of operations over here. Remember, without chaining, it looked like this. All instructions, no instructions, no two different vector instructions can be pipelined. Whereas here, we're pipelining these vector instructions over here. OK. Now let's improve them. Well, I guess I've given you the answer over here. These two vector loads, even though they're independent of each other, they cannot be pipelined. Why? Well, because you have only one port. Here, I've already given you the answer. Again, these two, while you're doing this vector load, you can do this vector store. Because this loads from vector register B. This loads from, stores into vector register C. And while you're loading vector register B's later elements, you're storing vector register C's earlier elements. You could potentially pipeline them, but they cannot be pipelined because you have only one port to memory. So let's fix that problem. This is the memory bandwidth bottleneck in a vector processor. If you add more ports, you can parallelize more operations. Now let's assume chaining and 2 load ports and 1 store port in each bank. So you can do these 2 loads in a pipeline manner. And now you can do the store in a pipeline manner, which means that 2 load ports means that you can start this load, and you can keep this is the load of the first load of A into vector register 0. You can start the first access over here. And in the next cycle, you can actually start not only the next access of this vector register, but also the next vector load. Because you have 2 ports. One port in each bank is satisfying this vector load from A into vector register 0. The second port in each bank is satisfying this vector load from B into vector register 1. OK? Now, the downside is now you have an expensive memory system, right? You need to have 2 ports into each bank. And in the same way, you can actually perform the store while you're doing this load. Although in this case, you may not need to do that because these are already overlapped. Oh, you do actually. There's some overlap. OK? So this takes you down to 79 cycles, which is nice, right? So you can see the effect of a good memory system. It doubles your performance compared to a bad memory system. And 79 is much better than 1504, right? I guess everybody will agree with that. OK. OK. Any questions so far? Everybody likes vector processors now? No? OK, you can do some exercises from the exams in the past and from your homework also. There are a bunch of questions. Now, this is actually a great model, but still strict. So how do we actually make it less strict? One is, what if number of data elements is greater than number of elements in a vector register? Well, an instruction can only operate on the maximum vector length, which is determined by the maximum number of elements that can be stored in a vector register, right? If this is the case, if you want to operate on, for example, 1 billion pixels, whereas your vector register is 64, well, you need to break that loop so that each iteration operates on the number of elements in a vector register. That's kind of obvious, right? An example is here. If you have 527 data elements for some reason, and you have 64 element vector registers, you basically have 8 iterations where vector length is 64. And you have 1 iteration where you need to change the vector length to 15. That means that there needs to be some operation that changes the vector length software. This is also called vector strip mining, or really strip mining the loop. OK, this is simple, right? Another, perhaps more interesting question is, what if the vector data is not stored in a strided fashion? You still do the same operation on many elements, but those elements happen to be located in random places. And this could happen, right? Especially if you have indirect accesses, right? If you have irregular memory access to a vector. Well, the idea is use indirection to combine and pack elements into vector registers. This is employed in many vector processors today. This is called scatter-gather operations. When you do a load, you gather those elements from different parts in memory into a vector register. When you do a store, you scatter them back to those different parts in memory. Of course, you really need to know where they are in memory still. But that's obvious, right? You have to know where data is in memory. That's the idea, gather-scatter operations. This makes vector processors a lot more programmable. Let's take a look at that. This is one example over here. Let's assume that we have a loop like this. Why do we need something like this? We have a loop like this, and it has an indirect access. Instead of accessing array C with the induction variable directly, we actually access through an indirection. This D, array D, is the index array, if you will, that specifies which locations in array C should be operated on. Right. So you can implement this with a gather instruction, this load of C with a gather instruction. It's called an index load, in other words. First, what you do is do a vector load from this D, register D, that contains the address of D, into a vector register D, let's say. And then you do this gather operation, load indirect from register C base. OK? We'll see what that does. Basically, what this does is, in the memory system, you take register C and add to it all of these different addresses or indices that are specified by register D. OK? And then the rest is what we've seen before. You can load the B vector simply. You can do the addition after that, and you can store into A. OK, let's take a look at that. Basically, this is when is this useful? When your matrix looks like this, right? When a lot of your data looks like this. If you have lots of zeros, sparse matrices are one example data structures where this is used, and many scientific programs use sparse matrices. Basically, vector loads and stores use an index vector, which is added to the base register to generate the addresses. It's simple. Well, OK, let's not go this. For example, let's assume that we're going to store this vector. This is in a vector register. Vector register length is 4. And we're going to store this in an index way. We are going to scatter them to memory. And this is the vector that's used to specify the locations as offsets from the base register where these data values will be scattered to. This is your data vector. I assume that this is number 1. If this first vector, first value, first element of the vector is scattered into location index 1 from the base address. I assume that this is location at index 1. The second element is scattered to location in index 3, which means that in between there is nothing, right? 1, 2, 3. The next element is scattered to location in index 7. 1, 2, 3, 4, 5, 6, 7, 8. I guess that I made a mistake here, huh? Is that true? How many elements are here? 0, 1, 2, 3, 4, 5, 6, 7, 8. Huh? Let's fix this. Can I fix this? Say it again?
You didn't zero index.
I didn't zero index. Does that fix the problem? Let's fix this problem now. Yeah, I have an extra 0 still, right? Ah. All right. I guess let's not have a 0 index. But this will fix the problem, right? Oh, man. All right. I'll fix this problem. Somehow. I'll have to fight with PowerPoint a little bit, but oh, there you go. Does that fix the problem? It does, right? OK. So now let's see. This is index 1, index 3, 4, 5, 6, 7, 8. There you go. OK? This is scatter. Basically, if this is in your vector register, if you just scatter using this index vector, this is what you would get. If you really want to fix a 0 index, I have a solution for that. 0, 2, 6, 7. Does that make everyone happy? OK, good. Now everyone got it, hopefully. OK. If you want to load from this, basically you supply the same index vector and do a gathered load. OK. So that's one thing that improves programmability. The second thing that improves programmability significantly is to allow conditional operations. That's through the vector register, vector mask register. And I guess I'll describe this, and then we'll take a quick break. So what if some operations should not be executed on a vector based on a dynamically determined condition? This is one example. I use goto here. Don't ever use them, but I just use them for illustration purposes. Basically, you multiply array AI and BI and store the result into BI only if AI is not equal to 0. How do you implement this? Basically using mask operations. A vector mask register is a bit mask determining which data element should not be operated upon by a vector instruction. So this is the code that implements this, basically. You load the vectors, and you set the vector mask. Vector mask is set by checking whether vector 0 is not equal to 0. Basically, the coming operations should be executed only if the elements are not equal to 0, right? And this vector multiply that happens later is the same thing. It operates on vector 0 and vector 1, but only those multiplies that satisfy this vector mask condition for whom the vector mask bit is set will take effect. Every element for whom the mask is not set is set to 0. You won't do the multiply. Does that make sense? It's simple. And then you do the vector store. And this is, as I told you earlier, this is essentially predicate execution. Basically, what you're doing with this vector mask is you're setting the predicate bits for every element in the vector registers that you're going to operate on later. And you can imagine having more vector mask registers. You can have a vector mask register 1, 2, 3, 4, 5, and then you can keep doing conditional operations. OK. So another example over here with masking. I'm not going to go through this in detail, I guess, but this shows you that a more complicated example. Basically, if AI is greater than BI, then you copy AI into CI. Otherwise, you copy BI into CI. How do you do this? Well, you first compare A and B in a vector way to get the vector mask. And vector mask looks like this. And then you first store A into C, and only those stores that satisfy the vector mask or satisfy this condition will be done. Everything else will not be done because they're set to 0. Now to do the other else part, what you can do is you can complement vmask, vector mask register, and you can do the store of C into B. Okay? So you can actually do operations on the vector mask register also. Okay, so how do you implement this? Basically, the simple implementation, vector mask basically means write enable in one sense, right? Do you do the operation? One way of implementing it is you can perform the operation. In this case, these are adds, or some operation, I guess. And this is the mask value for each element. And this is what's coming out of the pipeline. You compute a value for each of them. But in the end, you set the write enable bit to memory or register, right? And mask can basically simply be the write enable bit to the memory or register for the destination. This is kind of wasteful, right? Because you're sending all of the vector, the entire vector, into the pipeline, even though some of them will really not take effect. Because some of them have mask bits, some elements have mask bits that are zeros. But this is really simple. What you can do is basically send with each element of the vector the mask bit also, and the mask bit simply says, are you going to write the result back to memory or not, memory or register or not. The more complicated implementation is called density time implementation. You can have some logic that looks at this mask vector, scans it, and only executes operations on the elements with non-zero mask bits. Right? Here, for example, you don't need to execute this operation. You don't need to execute this one. You don't need to execute this one. You don't need to execute this one. So there's some logic that checks the mask bits and sends to the functional units only those operations for which the mask bit is 1. That's a little bit more complicated, of course. You need to scan this. Right? Yes?
In the previous slide, if you have an else, won't you have to do the thing, like, won't you have to pass all the elements through the pipeline again? When you complement the mask bits and then do the else part?
When you do this part?
Yeah.
Which elements do you need to pass again?
Won't you have to pass the whole vector again? Because you're basically operating on the complemented masks.
That's right, exactly. You do need to pass the whole vector. But what you can do is you can actually have some logic that does this, right? Yeah. If you have this logic, you don't need to pass the entire vector. It really depends on this implementation. That's why I'm showing you this. OK. I think let's take a short break here, and then we can continue with these issues. Let's be back. I said that memory system is a very important part. I've already talked about this issue, but people have optimized this a lot. Basically, the number of banks that you want to have is really related to the stride. Right? And if you're doing a vector load access or vector stored access, as long as the stride is relatively prime to the bank, number of banks, then you're good, right? What does relatively prime mean? Well, these two numbers, the stride, the value of the stride, and the value of the number of banks, they cannot divide each other, right? Does that make sense? Or their greatest common denominator is 1. That's a fancy way of putting it, I guess. OK. Well, I guess there's one other thing, of course. There should be enough banks to cover bank access latency. Right? These two ensure that consecutive accesses for a single vector load or store proceed in parallel or in a pipeline manner across the banks. So for example, if you have a stride of 1 and 16 banks and a memory access latency of 11, then this is good, right? Because consecutive elements come from different banks. If you have a stride of 4, 16 banks, and memory access latency is 11 cycles, it's kind of bad, right? Because the first element comes from bank 0. Assume that that's the case. The second element comes from bank 4. The third element comes from bank 8. The next element comes from bank 12. The next element comes from bank, I guess there is no 16 in this case, 0 again. right? 4, 8, 12. Now, if your memory access latency is 11, by the time you need to load the 5th element, this bank 0 is still servicing the 1st element, right? Because these two are not relatively prime, and I guess this memory access latency is long, you get this bank conflict. Element 0 conflicts with element 5 because they happen to map to the same bank. Okay? Now, if your memory access latency was short, this may not be a problem, right? For this particular load, at least. If your memory access latency was 4 cycles, by the time you need to load element 5, this access would have finished because you've started this in 1st cycle, 2nd cycle, 3rd cycle, 4th cycle, and 5th cycle. This is done. You can access that bank again. But usually, our memory access latency is not even 11 cycles today, right? It's in the order of hundreds of cycles. So mapping your data such that your stride is relatively prime with the number of banks enables you to make use of your memory bandwidth fully. And this is very important. Now, we'll later see this problem in caches. Because what happens here is you're really getting a bank conflict, right? 2 accesses go to the same bank, and they need to access the same bank at the same time. And to avoid this conflict, you can either map your data nicely or do things like randomizing of the address, right? You can actually have a circuit that takes the input address. In hardware, you can determine the bank address, right? And you can try to map this input address, maybe hash it with some value, for example, in this randomizer, let's say. Of course, it needs to be predictable randomizer. The same address needs to always go to the same bank, right? You cannot just generate a random bank address over here. To minimize the number of bank conflicts. And this was actually explored in the context of vector processors for a long time. There's a really good paper by Bob Rao on pseudo-randomly interleaved memory that I would definitely recommend for those of you who like matrices, for example, because he goes into, this is in ISCA 1991. Basically, he looks at the design of this randomizer and tries to figure out something that minimizes the bank conflicts. And this design of the randomizer consists of a lot of matrix operations that basically randomize the address. OK? So there are multiple ways of reducing bank conflicts. But the best way is actually for the programmer to, well, best way that puts a lot of burden on the programmer is to have the programmer do this mapping nicely. But that mapping becomes very complex because it's not only this vector maybe, but maybe other vectors accessing memory at the same time, right? So storage of a matrix, this is something that I would like to talk about because this affects your stride significantly. There are 2 ways of storing a matrix. You may have seen this in 213, row major versus column major order. Have you guys seen this? OK. So you can answer any question that I ask about this. Maybe. Who knows, right? Hopefully you will. Say it again? Maybe. Well, you'll definitely answer the questions. OK. Row major. Row major means that consecutive elements in a row are laid out consecutively in memory. So I'm going to go through this quickly since you know this. Column major, well, these are rows and columns of a matrix. This is what I've shown you over here. These are the rows, and these are the columns. Row major means consecutive elements in a row are laid out consecutively. Basically, element 0 is in memory 0, memory location 0. Element 1 is in memory location 1. 2 is here, ... Basically, row is laid out consecutively. Column major is the opposite. In this case, the consecutive. Wait a second. Did I do that right? Consecutive elements in a row are laid out. Yeah, that's right. I didn't mess it up. In the second one, column major, this is easy to get confused about. Consecutive elements in a column are laid out consecutively in memory. Basically, it's not this, but it's the same array can be laid out this way. Consecutive elements in a column are laid out in consecutive locations, right? And this determines your stride. So let me show you. If you can access a row major laid out matrix in a column major way, in which case your stride is different. from the case where the same matrix is accessed in a row major array. So it depends on your access pattern, right? Your stride depends on your access pattern. And you need to change the stride when accessing a row versus column, right? Regardless of however you store the matrix, unless you store it in both formats, which is actually difficult also. So this is an example. I'm not going to redraw this, but this is similar to what I've shown you earlier. Let's look at matrix multiplication. And you have two matrices, A and B. They're both in row major order, which means that consecutive elements in a row are laid out consecutively in memory. And they're from this base, which is A0 and B0. And we're going to multiply them. A is a 4 by 6 matrix. B is a 6 by 10 matrix. So the result is a 4 by 10 matrix, right? So in order to do this multiplication, first we need to load A0 into vector register 1. And each time you need to increment the address by 1 to access the next column, right? So first matrix accesses have a stride of 1, right? Whereas to do this, you need to load B0 into a vector register V2, but you need to load a column of this, which means that the consecutive elements that you need to access are 10 apart from each other, right? Which means that you have a stride of 10, right? So you need to set the stride based on how you're accessing it. But you may access this array B with a stride of 1 also, if you're multiplying this with something else, for example. And these different strides actually lead to different bank conflicts. So if you're accessing these two or some other array with different strides, now you get other bank conflicts if you can support multiple loads in parallel. Then the key question is how do you minimize them, and we briefly discussed that. OK, let's revisit this array versus vector processors. Let's try to build a modern processor with this. As I told you earlier, array versus vector processor distinction is the purest distinction. Most modern SIMD processors are a combination of both. They exploit data parallelism in both time and space. And this is what an array processor looked like. This is what a vector processor looked like, if you remember. This is vector instruction execution in a traditional vector processor. You have one functional unit that looks like this, and you pipeline the operations in consecutive cycles. But if you have multiple functional units that combines an array and vector processing styles, if you will, this is what it looks like. Basically, you do the first 4 operations in parallel, or 4 operations in parallel, and this could be an add, 4 adds in parallel, and remaining adds in a pipeline manner in the different functional units. Does that make sense? Element 0 is added upon here. Elements 1 are added upon here. Elements 2 are added upon here. Elements 3 are added upon here in parallel. And the remaining, the next 4 elements are added upon in parallel. The next 4 elements are added upon in parallel, dot, dot, dot. Right? If you look at this, this looks like both a vector processor and an array processor, right? You're basically partitioning your data across different functional units. Or in other words, the data elements that are added upon here are satisfying the property that the index modulo 4 is 0, right? In this case, index modulo 4 is 1, index modulo 4 is 2, index modulo 4 is 3. OK? That's simple. So a vector unit is structured such that elements 0, 4, 8, 12, 16, 20, 24 are supplied by a register file that contains only them. Elements 1, 5, 9, 13, blah, blah, dot, 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 are supplied by a register file that contains only them. So you can partition your register file now. That's what a GPU looks like. Actually, GPU looks like this, basically, internally. Your functional units that operate on elements 0, 4, 8, dot, 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 are connected to the register file that contain only those elements. This is called a vector lane, if you will. And these are the vector registers. So different vector registers, all vector registers are here, but only the elements 0, 4, 8 are here. Only the elements 1, 5, 9, dot, dot, dot are here. 2, 6, 10, dot, dot, dot are here. This enables partitioning of the register file, which is good, because now not your entire register file needs to be connected to all of your functional units. Right? You may have a huge vector register, vector length, but not all of it needs to be connected to all of the functional units. But this also reduces your programmability now if you want to, for some reason, operate on element 1 over here, well, too bad, you cannot, right? It needs to be, the data needs to be mapped. This function unit cannot operate on this register file. This function unit cannot operate on this register file. Make sense? OK. So this combination of array and vector parallelism enables a lot more parallelism. Now you can overlap execution of multiple vector instructions also. I'll give you an example. This is very simple, so I'm not going to go through this. It's an example machine that has 32 elements per vector register and 8 lanes. If you have 3 units, and if you can do multiple vector instructions in parallel, you can complete 24 operations per cycle while issuing 1 short instruction per cycle. Well, this is what it looks like. A load, basically, in the first cycle operates on the 8 lanes. And because you have 32 elements per vector, it takes 4 cycles. A multiply does the same thing. An add does the same thing. And you're doing 24 operations per cycle. OK? So it's nice. I like looking at these colorful pictures. OK. This takes us to something that people have tried to do for a long time. And it's a very tough thing to do for irregular programs, which is automatic code vectorization. If someone writes some code, can you automatically parallelize it? Now, this is nice. You can do it here. Basically, for this to work, the loop iterations need to be independent of each other, as we've seen, right? The key question is, can the compiler somehow figure out that loop iterations are independent of each other? Now, this turns out to be tough because of the exact same problem that we've discussed. Compiler doesn't have information about some things. And memory address is one of them. Does this store overlap with this load? In this case, you can tell, because I is not changing in the middle. And yeah, I guess even this store needs to be, the compiler needs to ensure that CI does not overlap with AI and BI, right? Even here, the compiler needs to ensure that. If compiler does not have that information, it cannot automatically parallelize the different iterations of this loop. But let's assume that you have that information. If you look at this, this code executes. I'm going to omit the branches here, like this, sequentially. This is 1 loop iteration, 2 loads, 1 add, and a dependent store. 2 loads. This is the next iteration, 2 loads, 1 add, and a dependent store. Assuming that these loop iterations are independent, you can actually lay this iteration next to this iteration, and you get this. Now you can do the iterations in parallel. And now you can vectorize by combining these loads together. Now, loads are operating on different data elements, but they're the same load, same operation. This is how you can actually form vector instructions, by putting multiple instructions together, right? OK. Basically, vectorization is a compile time reordering of operation sequencing. Right? Instead of having this iteration sequenced after this, you reorder the operation sequencing. This requires extensive loop dependence analysis. And one example, even this very simple loop requires dependence analysis to ensure that you're not overriding AI and BI when you're writing to CI. Right? Basically, the range of CI should be outside the range of AI and BI. Right? OK. Let's see. We still have time, right? I'm going to finish at a nice point. Vector machines are good at exploiting regular data parallelism because same operations are performed on many data elements. This improves performance and simplifies design because there's no inter-vector dependencies. Right? The downside is performance improvement is limited by the vectorizability of code. And I'm going back to the Cray I example. Scalar operations limit vector machine performance. Right? If you have, let's say your vector length could be infinite. If scalar part of your code is 1% of the entire execution time, the maximum speed up you get is only 100, right? That's Amdahl's law. Because 99% you can perfectly parallelize, but that 1% ensures that your maximum speed up is only 100, even with infinite number of functional units. That's exactly the reason Cray I was the fastest scalar machine at its time. This is also called the sequential bottleneck. If you think of vector operations, they're parallel, whereas scalar operations, they're sequential. So this is the sequential bottleneck. So vector machines have affected lots of things. So many existing ISAs actually include SIMD operations today. or vector-like operations today. I'll give you an example, and then we'll conclude today's lecture. But obviously, GPUs we're going to start in the next lecture. And GPUs are basically what I've shown you kind of here. Well, not here, but in the previous slide. I'm not going to go back to it. But with one key difference. If you look at the readings, you'll see. So many existing ICs include SIMD operations. I'm going to show you an example from a very old, the first edition, Intel's MMX, multimedia extensions. Now it's improved to, oh yeah, AVX, that's right. I always forget to remember its name. AVX, Advanced Vector Extensions, I think. But pretty much all ISAs have this, vector extensions. So let's take a look at one example. Intel Pentium introduced MMX operations to accelerate essentially multimedia processing. The idea is the same as an array processor, actually. Well, not quite, but it's a limited form of array processing. One instruction operates on multiple data elements simultaneously. It's similar to array processing, yet it's much more limited. And it was designed with multimedia graphics operations in mind, such that you can operate on multiple pixels and multiple granularity of pixels. So if you look at this, you can treat a 64-bit data element in multiple different ways depending on the type of the instruction. There's no vector length register, so it's not programmable. You have to use different instructions to do different SIMD operations. This is the original operation, scalar operation. You can treat a 64-bit data element as a 64-bit quad word. Or you can treat it with a different opcode instruction as two 32-bit double words, or as four 16-bit words, or as 8 8-bit bytes. Think pixels over here. Pixels are 8 bits. So you can actually add 2 pixels together, for example, if you want to do that. If you want to do averaging, for example, for some reason. This actually is a very nice paper that discusses the development of MX technology. And a lot of the figures that I'm going to use in the next few slides come from that. And stride is always equal to 1. So if you want to do a vector load or MMX load, I shouldn't call it a vector load. It's really an MMX load. Then your stride needs to be equal to 1. So it doesn't have gather, scatter operations. It's very limited. Let me give you an example of why this is useful. Let's say, assume that we have this picture, and we have this background picture, and this is what we would like to achieve. This lady has a background over here that's blue. Pretend that that's blue. Oh, I guess this is the image that I got from the PDF file. And we're going to replace and assume that the lady isn't wearing blue anywhere, and her eyes aren't blue. What we're going to do is replace every blue pixel that we see with this image with a pixel in this, well, tree and flower, I guess. You got to use your imagination here. And we're going to get this. Now, if you do not have any vector operations, if you have only scalar operations, what you need to do is basically a for loop, right? For I less than the width, j less than the height, ij, check if pixel at ij is blue. If the pixel at ij is blue, change the value of that pixel in memory to this pixel over here, right? That character over here. Basically, it's a lot of operations. Whereas with MMX, what you can do is you can operate with on 8 pixels at a time. Basically, you can load this into a register called MMX register 1 in this case. And you can do this operation that looks ugly. It's a packed compare equal byte operation. What you're doing is, assume that this is, well, let's see. No, this is where we're going to load the image. We've loaded 8 bytes of the image into MM3. We're going to compare it to blue. Basically, you set a register to all blues, but this is basically the code for blue in a pixel. And I don't know what that is, but you guys may. And what we're going to, this is the part of the image that's been loaded into MM3, and assume that this is not blue, not blue, 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 not blue, not blue, blue, blue. I guess one question could be, where is this 8 pixels taken from in this image? But I don't know. It must be somewhere around here, right? It definitely is not here because this is all blue. OK, this operation, what it does is it compares in a packed manner byte, every single byte in the 64-bit word of these two 64-bit words, and outputs a mask. And mask is basically, if this 8-bit is equal, if these two 8 bits are equal, then you get all zeros. Then you get all ones. Otherwise, you get all zeros. Make sense? It's a bitwise comparison, actually. And we're comparing 8 bytes over here. Eventually, we get all zeros for these 2 pixels, all ones for these 2 pixels because they're blue, all zeros for these 2 pixels, all ones for these 2 pixels. Make sense? And these are 8 independent operations that are done in parallel, right, by this instruction. Now what we want to do is, now we've figured out that whether or not this base image, what pixels are blue. Now what we want to do is to replace those pixels that have evaluated MM1 to all FFs with pixels from here, and otherwise do not disturb this image at all. Right? And that's what these other cryptic operations do. There's a packed end. Well, at the end of this operation, we have MM1 indicating whether the pixel is blue or not blue. This packed end, what it does is it takes the values. This is MM4. And MM4 is 8 pixels coming from this blossom image, apparently. If you read this, you see that it's a blossom image. These are 8 pixels coming from that image. MM1 says whether or not the corresponding pixels from this lady's image are blue or not. Basically, we're packed ending these two. And everything that's zeros will set the resulting pixels to zeros. OK? So these basically set those pixels that are blue to the pixels coming from the blossom image. And we do another packed end not over here. Everything else should come from the lady's image, right? So the pixels that are blue in the lady's image should be replaced with this other image, blossom image. The pixels that are not blue should be replaced with whatever the pixels were in the lady's image. So this way, we get parts of the pixels, what we should not replace, and we get the pixels that we should replace. And now if we OR them, we get a combination of both images. Right? It's actually simpler than what I described, but it's kind of hard to describe, I guess. OK? And this is the code. This is the end resulting code. You have moves load 8 pixels from the lady's image. You load 8 pixels from the blossom image. And you do a pack compare equal byte. You do a packed end not, and packed OR. This way, you replaced 8 pixels. OK? Any questions? Yes?
It seems like you're very limited by the ISA in terms of what you can do on these longer registers.
Absolutely. Yeah, this is very limited. This is I would not call array processing or vector processing because you don't even change the vector or the stride. But it's a very limited form of SIMD operation that still gets some efficiency. Right? Instead of operating on a pixel at a time, you're operating on 8 pixels at a time. So you can improve your efficiency roughly by 8x.
If you're doing exactly the right operation.
Exactly, yes.
They actually support, yeah.
Exactly. And you're removing some branches also, which is nice too. Right? OK. And they have actually quite an extensive set of operations with the recent AVX extensions. You can take a look at them. So this will be much more efficient in terms of operating on longer vectors. And we'll see that we'll see GPUs in the next class. OK. I guess I'll let you go. I'll see you all on Wednesday.